Well, hello, happy Friday, happy first day of probability, and happy homecoming day. I'm so excited for you guys. I hope today and this weekend is so much fun. But before you get to all the festivities, we do have a quick day of notes to get through with our first day of probability. So here's our calendar. Hopefully you guys downloaded this from Schoology. You have this on your iPad and you're ready to go. Before we get into probability next week, we first need to learn how to count. So we're going to go back. We're going to look at this new way of counting for probability for the first couple days. And then next week, we're going to look into actually then how to compute probability. Notice we have a couple half days, no school, 2 quizzes, and a test in this chapter. So this will bring us all the way through Halloween to the first couple days of November. So this will take us our whole month of October. Okay, let's go ahead and get started. So the way we count when we're calculating probability is looking at permutations and combinations. And these are ways that we can count how many options we have in a certain situation. So before we can get to the counting, we need to make sure we know what we're looking at. We can have independent events and dependent events. So independent events are events that do not affect each other. Okay, so for example, rolling a die and then flipping a coin. If you roll a 2, that has no effect on what, if you're going to flip a head or a tail when you flip the coin, right? So rolling a die followed by flipping a coin, those are not affecting each other. So those are independent events. Dependent events, on the other hand, are events that do affect each other. So for example, if you have a deck of cards and you choose a king of spades from the deck and you don't put it back, so you have it in your hand, and then you go and pick another card, by picking the king of spades, that changes the number of options you have for the next card that you could possibly pick up. And so those events do affect each other. Okay, so what we're going to look at is having that kind of in the back of our mind. We have this basic counting principle, and it is this basic counting principle here, and it's a principle we can apply with independent events. Okay, so events that do not affect each other. So basically, if we have one event that can be chosen m number of ways, and another independent event that can be chosen n number of ways, then the 2 events can be chosen in m times n different ways. Basically, we take the number of ways, number of options we have for each event, and then we just multiply them together to get our total number of options. Okay, it makes sense with this basic example. So let's say you're in the lunch line and you have a choice of 3 entrees. Okay, so that's in red. So we have 3 entrees: chicken salad, turkey sandwich, or grilled cheese. Then you have 3 sides. So you can then choose chips, french fries, or a fruit cup. And then you have 2 drink options. So you can either get a pop or a water. We can't say soda, so I don't know. I'm a pop girl. Okay, so pop or water, we'll say. How many different lunch combinations can you make? And so one way to get a visual idea of what's going on here is we make this tree diagram here where we take our 3 entree options and say, okay, if we get a chicken salad, we can either get a chicken salad with chips, chicken salad with french fries, chicken salad with fruit cup. And then with each of those, we can even go one step further. Okay, I can get a chicken salad with chips and a pop, or I can get chicken salad, chips, and a water. That's 2 different lunch options. Or we can get chicken salad with french fries and a pop, or chicken salad with french fries and a water, and so on. You'll see that if we were to go through these branches, we have 18 different total combinations. Now, luckily, I put this here for you. Could you imagine having to write this out every single time? This would take a really long time. The idea, though, the basic counting principle says that if we take every event, so the number, which entree we choose, and then we look at the number of sides that we can choose, and then we look at the number of drink options that we have. The basic counting principle says, hey, these events are independent of each other. What you choose for your entree doesn't have any effect on what you choose for a side. And what you choose for a side doesn't have any effect on what you choose for a drink. These are independent events. And because they're independent events, the basic counting principle says we can just take the number of options for each of them, multiply them together, and we'll get the total number of combinations. So the basic counting principle takes away this necessity. We don't have to draw out this tree diagram. It's way faster to just take the number of options for each choice, for each event, multiply them together, and then we get the total number of combinations, okay? So let's look at this next example. It says, how many outcomes are possible if you toss a coin, then roll a die, and then spin an 8-colored spinner? So notice, these are all independent events, right? When we toss the coin, whatever we get, and remember, what are those options when we toss the coin? We could either get heads or tails, right? H or T, heads or tails. So we have 2 options for flipping a coin. And then we roll a die. Now notice these are independent. What we flip, if we flip a head, that has no effect on what we're gonna roll when we roll the dice, right? A die is 6-sided, so there are 6 options. Okay, so rolling a die, we have 6 options, 6 possible outcomes. And then the last one is spinning a spinner. Now this spinner is an 8-colored spinner. So pick 8 colors. That's our total number of options that we have when we spin the spinner. So we have 8 total outcomes, okay? 8 total options, let's say. So because all 3 of these are independent of each other, they don't affect each other, the basic counting principle says we can take the number of options, which is 2, 6, and 8, right? 2 possible outcomes for flipping a coin, 6 possible outcomes for rolling a die, 8 possible outcomes for spinning the spinner, and all we have to do is multiply those together, and we have 96 different possible outcomes. We have 96 possible outcomes. Now, thank goodness for this basic counting principle, because again, could you imagine making the tree diagram with 2 options, 6 options, and then 8 options? Our tree diagram would be huge and kind of a pain in the butt to draw out. So this basic counting principle is really, really nice, okay? So you try. Here's our last example for this one. It says a student must take a history, a math, and an English class. There are 8 different history classes, 5 different math classes, and 2 different English classes. In how many ways can his schedule be accomplished, right? So again, does what the student takes for history, where there's 8 different history courses, does that have any effect on the math class that he chooses, which there's 5 different math classes? And does the math class have any effect on the English class? No, these are all independent events. So go ahead and find out the total number of possible class combinations this student can have. So because they're all independent, all we have to do is take the number of options, 8 history, 5 math, 2 English, multiply them all together, and we get 80 possible ways to form a schedule, okay? Not to mention then in what periods these are all offered, right? And then if you throw that in, then that makes the number of possible schedules way larger and way harder to figure out. So be really nice to your counselors, because this is what they have to figure out when you guys are doing your scheduling soon. There's so many different ways to figure out. And then multiply that by how many students there are, it gets crazy. Okay, so this is the basic counting principle. Again, we just take the number of options for each possible scenario and then just multiply them together. But remember, this only works if the events are independent, okay? All right, let's look at the next topic. So this is factorial notation. So we use this when they're not independent. So in other words, when they're dependent on each other. So when you make your first decision for your first option, that affects your decision for your next option. So for example, This says, and how many 5-letter words could we make out of the letters in the word table if we can only use each letter once? So notice in the word table, we have 1, 2, 3, 4, 5 letters. Okay? They want to know how many 5-letter words can we make out of those. So what we do here is we use something called the slot method. So the slot method says you make the number of slots you need. So we're making 5-letter words. So we're going to do 5 slots. 1, 2, 3, 4, 5. And decide how many options there are for each slot. And then you write those numbers here, and then we're just going to multiply all those together, and that'll give us our total number of outcomes. So look at how this changes. For our first slot, for the first letter of the new word that we're going to make, we have 1, 2, 3, 4, 5. We have 5 options. We could put a T here, we could put an A, a B, an L, or an E. So we have 5 options for this first slot. But once we choose one of these letters, let's say we put a T in the first spot, how many options do we have for the second spot? Well, now there's only 4 letters to choose from. Let's say we put an E there. Once we place 2 letters in the first 2 spots, now we're only left with 3 letters for the next slot, and then you guessed it, 2, and then 1 letter for that last slot. So because they're dependent on each other, the number of options changes for each consecutive slot, and they typically start decreasing by 1. And so the slot method says we just multiply those together, so 5 times 4 times 3 times 2 times 1, and we get 120 possible outcomes. So the words may not actually make sense, but there are 120 different ways we could organize these 5 letters into different words, okay? So when you take a number like 5 and you multiply it by all of the numbers that come after it in this order, that's called factorial notation, okay? So factorial notation, this product that we just wrote out, this is equal to 5 factorial. So if you see that exclamation point, in math it's not an exclamation point, it's not like we're saying 5 with an emphasis. We're saying 5 factorial, and that exclamation point means take 5 and multiply it by all the numbers that come after it. So that's called factorial notation. So a formal way to say it is, what if we have any number n, let's say? Well, factorial notation would say take n and multiply it by the numbers that come after it. So what's one number less than n? Well, n minus 1. What's one number less than n minus 1? Well, n minus 2. And we would keep going, because we don't know what n is, right? So we're going to keep multiplying all the way until we get down to 2 times 1, right? N factorials, you take the number and you multiply it with by decreasing by 1 all the way down till you'll get to 1. So for example, if 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, it's going to be really big. It's 5,040. Okay. Luckily, and this kind of takes a long time to type into your calculator, right? Luckily, our calculator has a factorial option. So on your calc, go ahead and write this down and look at your calculator, take it out. On your calculator, you press math, and then you're going to arrow over to probability. Yes, we have our own probability menu. And then option number 4 is the factorial. So if we were to do this, where's my calculator here? If we were to do this here and we would do 7 factorial, you type in 7, press math, arrow over to probability, you see option number 4 is the factorial, and it gives us the 5,040 right away. So our calculator will do that for us, makes it way, way easier. Okay, again, we use the factorial notation, and we use the slot method. We'll put it here. We use the slot method when the events are dependent, when they affect each other, right? So when they're dependent or when they affect each other. Okay, so let's see an example where we would use it. It says you need to make your schedule for next year. There are 8 periods and every class is offered each period. That would be like a dream come true, right? How many possible schedules can we make? Well, we have 8 periods to fill. So we need 8 slots. 1, 2, 3, 4, 5, 6, 7, 8. It says, so you have 8 classes that you want to take then, right? You have 8 periods, 8 classes. So you can choose. So when you're looking at what do you want to take for first period, you have 8 different options to choose for your first period class. But once you set your class for first period, now you only have 7 classes to choose from for your second period class, and then 6 for your third, and so on. So times 5, 4, 3, 2, 1. Again, this is the same as saying 8 factorial. So you could either type this in your calculator where we're multiplying all of these numbers down, or you can do 8 factorial in your calculator. Either way, you're going to get that there are, running out of room here, 40,320 possible schedules that you could choose from. That's a lot. Again, be kind to your counselors because there's a lot of different things at play here, a lot of different options. Okay, so let's try another one. Let's look at telephone numbers, for example. So telephone numbers, for these, this is tricky because for telephone numbers, does what the number you choose for the first digit of your telephone have any effect on your second one? For this one, actually, no. We can use the slot method for independent examples as well. So let's say you have a 7-digit phone number. So 1, 2, 3, 4, 5, 6, 7. We can put any digit in there. So let's think about our digits. How many digits do we have? Well, don't forget about 0. 3, 4, 5, 6, 7, 8, and 9, right? So we actually have, when you include the 0 in there, we have 10 different digits, okay? There's 10 total digits that we can choose from. So if we're taking a 10-digit phone number where the last digit has to be the number 4, this one has to be the number 4. So we only have one option for what the last number in the phone number can be. But how many options do we have for each of the other ones? Well, for the first digit of the phone number, we have 10 options. We could choose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once we put a number in the first slot and we look at the next slot of our phone number, are we limited on what number can go next? No, we still have 10 options for the second slot, 10 options for the third. We have 10 options for all of them, really. And so to find the total number of phone numbers we can have that ends in the number 4, remember, we only have one option for the last digit. That's the number 4. We would multiply that all out, and we would have a total of 1 million possible phone numbers. Okay. What about the total number of possible phone numbers if the first digit cannot be the number 2? So again, a 7-digit phone number where the first digit cannot be 2. So out of the 10 digits, we take away one option. So we have 9 options for the first digit. But then the other slots can be any of those 10 digits. So we multiply across here and we get 9 million possible phone numbers. That's good because there's a lot of people in the world, right? And everybody has a phone number. And then you throw in area codes into all of this, and then that's good because we have lots of people who need phone numbers, right? All right, so let's look at this one. The first 4 digits of our phone numbers, 1, 2, 3, 4, 5, 6, 7. They're telling us that the first 4 digits have to be 7, 8, 2, 3. Out of all the digits, there's only one number, that's the number 7. There's only one option, that's the number 8. That's a funky looking 8. There's only one option, that's number 2, one option, that's number 3. But then we have 10 options for the remaining ones. So here we have only 1,000 options. Since we're making it more specific, right? We're limiting what the first 4 digits can be. All right, what about this one? So 7-digit phone number, 1, 2, 3, 4, 5, 6, 7. They're saying that the phone number has to be divisible by 5. So what do we know about numbers that are divisible by 5? Well, numbers that are divisible by 5, they have to end, that means this last number, they have to end in 0 or 5, right? So we only have 2 choices for this last digit. But every other digit doesn't matter. We have 10 options for each of these. 10, 10, 10, 10, 10, 10, and times 2, and then we get 2 million for this one. Okay, so we have the slot method that helps us, and we really use the slot method a lot with dependent scenarios where the number of choices become limited based on what's in front. And the dependent, that's where we see, let me scooch this down, the factorial notation. But we can use the slot method with dependent or independent scenarios like phone numbers. So, but either way, it's still you put the number of options for each slot, and then you multiply them all together to get the total number of scenarios. Again, with this permutations, combinations, today's lesson, just kind of looking at first, how can we count the total number of options that we have for each scenario? We need to know how to count, so then next week we can calculate the probability. So your homework's worksheet 1, but make note of this. On worksheet 1, you can go ahead and skip numbers 7 through 15. We're going to complete those tomorrow or on Monday when we get back to class. Okay? Have an awesome weekend. We'll see you guys later.